Hello, everyone, and welcome to the VaNTAGe seminar. And we're continuing our series of talks on profinite groups and Galois groups. And today we're very happy to have Olga Lukina, who's going to be talking about Galois groups and the dynamics of Cantor actions. So, Olga, is it all right if we record this talk?
Yes.
Wonderful. And if you have questions, please feel free to ask them during the talk. Well, Olga, please go ahead.
Okay, thank you, Rachel, for the introduction, and thank both of you for the invitation to speak. It's great to be here. And I'm going to talk about dynamics and Galois groups. So my talk will be about arboreal representations of absolute Galois groups of number fields. And initially, I think at least the first paper which looked at them I'm aware of was in number theory, and the motivation for looking at this type of representations was to use it to compute the density of primes in certain situations. But these representations are actually separable profinite groups acting on the boundary of a tree, and the tree is a graph. So they also arise as certain objects in topological dynamics and geometric group theory. And my background is in dynamical systems, so this is what I'm interested in. I'm going to use or study dynamical invariants to study actions which arise from arboreal representations of Galois groups of number fields. Okay, so let me just start by describing what I mean by a rooted tree and how the actions I'm talking about arise in dynamics and also in number theory via arboreal representations. So as I said, the tree is a graph, and it is a rooted tree because it has a root here in my picture. This is the root. And the vertices of the tree are divided into levels. And the idea is that the root is connected by edges to d vertices. So we choose first an integer d. And the root is connected by edges to d vertices. And each next vertex is connected by edges to d plus 1 vertices. So this is one vertex on the previous level and d vertices on the next level. So a tree with such property is called a rooted tree. Also a rooted regular tree or rooted diary tree. So the terminology varies a little bit depending on what on papers in which area you read. Okay, so how do Cantor sets arise in this setting? Well, you can look at the boundary of the tree. So what is the boundary of the tree? So first of all, if I have two vertices in a tree which are connected by an edge, then there is a unique edge connecting these two vertices. So I can introduce notation for my edges like this. So the starting vertex and the ending vertex. Next, I'm going to look at all possible infinite paths starting at the root and going infinitely far away. So the space of such paths, I can give it a topology. And the standard way to do that is to define topology using cylinder sets. So what are the cylinder sets? A cylinder set is determined by a finite path from a tree to a certain level n. So for instance, I can choose one of the edges, for instance, this one, and then all the paths which pass through that edge, so that would be kind of paths here, they would form for me a cylinder set. And this is an open set in the cylinder set topology. And moreover, this set is not only open, it is also closed because its complement consists of open sets. So in dynamics or topology, we call such sets which are open and closed Kloppen sets. So I may be using this terminology later on. That's why I'm explaining it. Now the set of all paths in the tree is given a topology, and this is more or less a standard argument to see that this space is going to be compact. You can put a metric on it, and it's totally disconnected and perfect. Perfect means that there is no isolated points, so it is a Cantor set. Now, where do we find the dynamics here? So in dynamical systems, we usually work with actions of countable groups. So I will start with a countable group. So we want our countable group to act on the tree. And the action is going to be by automorphisms of this tree. And an automorphism means that the map which we define preserves the structure of the tree. So in particular, what does it mean in this setting? So first of all, we are going to act by maps which map vertices to vertices and edges to edges. And this is done in such a way that the structure of the tree is preserved. So if this means that if you have two vertices connected by an edge, then the image is also going to be connected by an edge. Also, if we restrict such an action to a finite level, so for instance, this would be one level, this is the second level, and so on and so on. So if we restrict such an action to a finite level, then this action is by permutations of vertices. And in addition, we are going to require that when we restrict our action to each level of the tree, then this action is transitive on this tree. So if I choose any two vertices, then by applying action by a sequence of elements in my group, I can get from one vertex to another. And this holds for any two vertices. So this is the action by tree automorphisms. Now, if you have an action like that by tree automorphisms, which restricts to permutations on each level of the tree, then we can also define an action on the boundary of the tree, so on the set of all infinite paths. And this is defined in a very natural and simple way. So basically, on the previous slide, I guess I didn't mention it, but on the previous slide, we require the action to be compatible with the structure of the tree. So if you have like a paths, this means that paths are mapped into paths. And because of that, we can extend this action to the boundary. So by just acting on each finite level. So if our group is countable, then the actions, the orbits of these actions are going to be countable subsets of the boundary of the tree. And remember, I required that when I restrict to each level of the action, then the restricted action by the permutation group is transitive. This results in an extra property of the action on the boundary, that the action on the boundary of the tree is minimal. And minimal means that every orbit of this action is dense in the Cantor set, in the boundary of the tree. Okay, so I started with a countable group, but to relate it to arboreal representations, I need a profinite group. So here, where a profinite group comes in, so the action on the boundary of the tree, which I defined, is an action by homeomorphisms. And what I can do next is I can check the closure of this action in the space of homeomorphisms of the tree. So checking the closure of the action in the topology of pointwise convergence, this is actually this closure is an old objects in dynamics introduced in 1950s by Ellis. So it's called the Ellis semi-group of the action. But in this particular setting, when we act on the boundary of the tree, the action has special properties. So it is equicontinuous, which means that it's more or less by isometries. And in that case, the semigroup actually becomes a group. And also the topology of pointwise convergence coincides with uniform topology on this space of homeomorphisms. And this way we get a profinite group called the Ellis group of the action. Now, because the action of the countable group on the boundary of the tree is minimal, the action of its closure, which is the profinite group, is transitive. So all our Cantor set is in a single orbit. Are there any questions so far?
No, it's great. Thank you.
Okay. So here is an example of an action like that, which arises in various disciplines, maybe under different names. So in dynamics, we call this action an odometer or the adding machine. And this is an automorphism of a tree which acts so that when I restrict to every finite level, then the restriction is the group is generated by one single permutation, which is transitive. So we can describe it in a slightly different way as follows. So if we choose a path in the tree and we start acting on it by the group generated by the adding machine, and this since we only have one element which generates the action, the acting group is going to be just the integers. So if we do that, then we can identify each finite level of the tree with z mod d to the power n z with a finite group. And the action of our adding machine on that would be just the addition of 1. And doing that for every level, what we will obtain is that the boundary of the tree as a topological space, it's identified with the dyadic integers, and the Ellis group is actually the group of dyadic integers. Yeah. So this is an example of a very simple action which turns out important later. Okay, so how arboreal representations arise as actions on rooted trees? So let us check a polynomial of degree d with coefficients in a number field called k, and let us fix a point. What we can do next is we can look at iterations of this polynomial, and we can consider the following equations. So we would like to have a situation when we have d to the power n distinct solutions for this equation. And since we're over a number field, we will just require that all polynomials f to the power nx minus alpha are irreducible. So, and what we are going to do is we are going to identify, so the root here is going to be alpha. For each n, we will identify the set of solutions of this equation here with the vertices at the same level of the tree. So here I would have all the preimages of alpha under the first iteration of the polynomial. Here, under the second iteration, and so on and so on. So I defined the vertices of my tree. I have infinite number of iterations and infinite number of levels now. And so now I have to say how I draw the edges. And I'm going to draw an edge between two vertices if applying my polynomial to one of them, I get the other one. So this is how I get a tree. Now, what is the action? What is the dynamics? So when we adjoin the vertices, so the solutions of the polynomial equation to the number field K, we get a finite field extension. And because of the assumptions we made, this extension is Galois. So in particular, we have a Galois group which permutes the vertices, permutes the solutions of this equation here, so the vertices. And since we get a nested sequence of field extensions, it turns out that the action of consecutive Galois groups on the level sets is compatible with the tree structure. So in this way, we get a sequence of actions of finite groups on finite levels of the tree, which are compatible with the tree structure. So then what we do next, we check the inverse limit of that. And we obtain a profinite group, which is called the image of the arboreal representation of the absolute Galois group of the number field K associated with the polynomial and alpha. Or I will just call this image group, actually, I will just call it arboreal representation for simplicity. So this Galois group, this profinite group is separable and it acts transitively on the Cantor set because, and the consequence, this is the consequence of the fact that the field extension we were looking at are Galois. Okay, so to the best of my knowledge, this type of type of representations of Galois groups first were considered by Adoni in the paper in 1985, and Adoni's interest was the following. So given alpha in the number field K, or I think Adoni just looked at the rationals, we can consider the orbit of this alpha under the forward iterations of a polynomial. So you can also describe it as a non-linear recurrence relation. And the question was, what is the density of prime divisors of the points in the orbit? And Adoni obtained a way to get an upper bound on this density by looking at kind of at the tree of pre-images which I just described. So, and recently this field has been getting more and more attention, more and more activities were happening. So for instance, there is a nice survey by Rafe Jones. But actually, at this point, now it's 2025, maybe the survey is a little bit already out of date because since then there has been lots and lots of activity in this field. And here I just have I have just a few names mentioned, but these are not all the authors which work in this field. And just like what kind of questions people ask when they look at arboreal representations. One of the questions is, for instance, for which polynomials, fields, and alphas, in what cases the arboreal representation has a finite index in the full automorphism group of the tree. So this is one of the questions considered. Now we have the same object arising in two a profinite group acting on the boundary of a rooted tree arising in two different contexts. In the context of number theory, when we are looking at arboreal representations, and also in the context of topological dynamics. and also geometric group theory. So when I first looked at this topic, it was not completely clear to me, for instance, how to go from one case to another. So, but turns out there is a very natural way to relate the actions of countable groups, which we study in topological dynamics, with the arboreal representations with profinite groups, which arise in the context of number theory. So, and how can we do that? So, as I told you on the previous slides, the arboreal representation is obtained as the inverse limit of sequence of finite groups indexed by natural numbers. So this means that this group is separable as topological space, and in particular it contains a dense countably generated subgroup. So what we can do is we can give this subgroup discrete topology, and this way we get a countable group whose action on the finite levels restricts to the same action as the action of the Galois group, and therefore the Ellis group of this action is identified with the profinite arboreal representation. So maybe a little bit of a difference in two settings is that in dynamics we usually start with a single group, we look at the action, and then we get a closure. So this is of course kind of a way to get a unique object. You start with a countable group, you get a closure for the given action. But if you start with an action of a profinite group, there is actually many different countable subgroups which generate for you the same profinite group. So this is the difference. When we go from a profinite group to a countable group, there is no unique way to choose this countable group. So this may present some difficulties, and in particular, if you want to look at the action of the profinite group from the dynamical perspective, what you have to look is invariance not of the action of the countable group, but the invariance of the profinite closure of the action. And I'm going to talk in the rest of my talk about this dynamical invariance. Are there any questions so far?
So, what's the role of alpha in this? Does this Galois group change a lot depending on alpha?
So for some choices of alpha, it may change, yes. So actually I will be talking a little bit about that a bit later. So it may change, but for most alphas, they would be isomorphic, if I understand the theory correctly. So maybe
great.
in a few slides, maybe it will be better, clearer.
Well, thank you.
Thank you for the question. Okay, so what kind of dynamical invariants we are going to be looking at? So first of all, what invariants under what equivalence? So in dynamical systems, we have a range of equivalences, and here we are going to look at the equivalence of an isomorphism. So what are two actions which are isomorphic? We have two groups, and in this setting, they may be discrete or profinite, so the definition doesn't change. And suppose they act on counter sets, on two counter sets. The actions are isomorphic if we have two things. First, we have a homeomorphism of counter sets, and we have an isomorphism of the acting group. And these two maps are so that they're kind of intertwined by the action. And this is what this condition says. So you can act by one and then map to another counter set, or you first map and then act. So this all should be compatible. So if you ever heard talks in dynamics, you maybe heard about the notion of conjugacy. Conjugacy is a slightly stronger notion than the isomorphism. Conjugacy means that you are looking at exactly the same group acting, but here we allow some like maybe twist by an isomorphism. Okay, so now suppose we have a group, a profinite group, acting on the boundary of a tree. So most likely there are some elements which fix some of the paths in the boundary of our tree. And these elements can be of two types. So the action on a neighborhood of a fixed point can be of two types. Either you have an open neighborhood of your point V, which is pointwise fixed by the action of the element G. So every point in some open neighborhood is fixed by the element G, which fixes the point V. Or maybe this doesn't happen. So this is the second alternative. So to define a dynamical invariant, we are going to look at the elements which with fixed points. So we choose a point, and we look at the elements which fix this point and how they behave on the neighborhood. And the neighborhood is not going to be fixed. The neighborhood is going to be getting smaller and smaller and smaller. So I guess I can say decreasingly smaller. This approach, this type of dynamical invariance, and this approach was introduced in a series of joint works with Steve Herder. And we like to think about this as kind of trying to study infinitesimal properties of the action in the case when we cannot differentiate, because the Cantor set obviously is totally disconnected, so we cannot check derivatives. But we want to have some kind of an analog of that. Okay, so what happens when we have group acting? By the way, how much time do I have?
Oh, you have another half hour, but you could also end earlier than that.
Okay, I should be fine. Okay, so now we have our profinite group acting on the boundary of a tree, which is a Cantor set. So we choose a point, and we are going to look at the isotropy group of this of the action on this point. So the isotropy group is the set of elements which fixes a given point. You can also call it a stabilizer. Again, there is no the terminology differs. We call it the discriminant group of the action, but of course, in algebra, we have discriminant of a polynomial. This has nothing to do with this discriminant group. So we have to make this disclaimer. Although this invariant, this group is defined as the set of elements fixing a given point, up to isomorphism, up to conjugacy, it's independent of the choice of a point, because we are in a situation when the profinite group acts transitively on the Cantor set, so there is a single orbit, and therefore all the isotropy groups are conjugate. Now, this group is a closed subgroup of our acting profinite group, and so therefore it can be trivial, finite, or it may be a profinite Cantor group. And now what we have is a homogeneous model for our action in a very classical way. And the advantage of looking at this model and looking at this discriminant group is actually, well, in general, the Ellis group of an action is very difficult to compute, but in this special equicontinuous setting, when we look at the boundary of the tree, it's actually computable, and using a tool called group chains. Okay, so now this is a little bit technical, but let's look at it. So now, So I said we are going to look at open neighborhoods which are getting smaller, smaller, and smaller. So what kind of open neighborhoods? So I told you earlier that the topology on our tree, on the boundary of a tree, is given by cylinder sets, and these cylinder sets are determined by finite paths. So for instance, if I choose a path like this, then all paths which with this beginning, they give me an open set. So this is what's written here. You're just looking at cylinder sets. And also, if I just look at this subtree of paths starting with the same finite bit, then this is also a Cantor set. Next, we are going to look at elements of our acting group G, which preserve this open set. So preserve, basically what is preserved, what it means is that this vertex is fixed, but the action may permute the paths within this open set. That's what I mean by preserve. And these elements form a Klopen subgroup of our profinite group. And also, this way, for our open cylinder set, we get a homogeneous model by dividing by the action of the discriminant group. Now, in this homogeneous model, you can describe the action of the discriminant group. You can relate it to the adjoint action of the discriminant group on this set of elements which preserve a given vertex, which preserve our given open set. And of course, we notice that if we have an element of the discriminant whose adjoint action at the nth level is the identity, then it will fix every point in the open set. So now using that, we can define two groups. So first, so we look at all the elements in the discriminant group which fix every point in our Klopen set in the tree. Among them, there are elements which do not just fix every point in the Klopen set, but their adjoint action is actually trivial. So these are two groups. And one of them is a subgroup of another one. So once we have these groups, we can define two direct limit groups by connecting these finite groups at each finite level. And this brings us to dynamical invariance, to a dynamical classification of actions of profinite groups. So first, we can show that the isomorphism classes of these two direct limit groups are invariants of the, so it should be isomorphisms here. Isomorphism, sorry about the typo. So these are invariants of the isomorphism class of the action. So we have two invariants. Now, but we can get more. We can compare these two invariants. So first of all, we are going to say that the direct limit group is bounded if eventually it stabilizes. So when we make the direct limit, the bonding maps are inclusions of our groups K, N, or Zn. So a direct limit group is bounded if these inclusions eventually become isomorphisms. So this brings us to a classification. We are going to say that a group action is stable if a group chain is bounded, and if it is not bounded, then the action is wild. So this may look at kind of a non-intuitive way to define stable or wild to you, but there is some motivation behind that, which I'm not going to talk a lot about, but the motivation comes from the questions of embeddability of such realization of such actions as actions on the transverse sections in attractors and exceptional minimal sets of foliations. And you can actually show that the boundaries of this group can be served as abstractions in certain embeddability questions. So this is the motivation under this classification. And in fact, you can, this is just kind of one step in a classification, but you can also look at various ways in which this group interact or differ, and you can define a final classification about that. And with my co-authors, we found a series of examples which show that all the possibilities are realized. Okay, but let us get back to arboreal representations. So now we have some invariants which tell us when actions are stable dynamically and when actions are wild. So do we have examples coming from arboreal representations? So there are some maybe simple examples. So if you look at this specific polynomial, over finite extensions of finite unramified extensions of p-adic numbers, and you look at the corresponding arboreal representation, then this action turns out to be stable. If you look at arboreal representations which are finite index in the full automorphism group of the tree, then such actions are wild. So these were the first examples I looked at. Now let us move to another series of works, and this maybe will answer the earlier question in a little bit more detail. Now we are going to move to pro-finite iterated monodromy groups. So what are those? So before our root was alpha, and it was an element in a number field. Now instead of that, we are going to take a transcendental element, and instead of the number field, we are going to look at the field of functions k of t. We also have a polynomial with coefficients in k, and we are going to make a very similar construction by looking at the iterates of the polynomial f and solving these equations. So everything works nicely. We get finite, we get Galois extensions, and we get Galois groups acting on finite level of the tree. So the inverse limit group, which we get by checking the inverse limit of this Galois groups of the finite extensions, we're going to call it the arithmetic iterated monodromy group associated to the polynomial f. And it turns out that in this group, you can find a special subgroup, which we call the geometric iterated monodromy group. And this is a normal subgroup of the arithmetic one. So now, to get to the arboreal representation, which I discussed earlier, we specialize by checking t equal to alpha. And it is known that, like in most cases, what we get is the isomorphism of this group. So I think the theory is that under specialization, the group cannot get smaller, and in most cases, it would be isomorphic, the same. Okay, so this is like a variant of arboreal representation, arithmetic and geometric iterated monodromy groups. Now, instead of looking at arboreal representations which have finite index in the full automorphism group of the tree, we are going to look at small arboreal representations. And what do we mean by small? So these are arboreal representations which have infinite index in the full automorphism group of the tree. And in particular, they arise if we look at post-critically finite polynomials. So what does post-critically finite means? When we have a polynomial, we have a set of critical points of this polynomial, and we are going to consider this polynomial on a Riemann sphere. So we add this point at infinity, and this point at infinity is going to be fixed. It's a fixed point of our polynomial. Now we are going to look at post-critical set. So this PC here, which I have, is a post-critical set. So we look at all critical points, including the infinity, and we look at the forward at the orbits at the forward iteration under the forward iterations of the polynomial. And a polynomial is post-critically finite if the set is finite. So basically, the orbit of every critical point, the post-critical orbit of every critical point is finite. So in the simplest case, when we have a quadratic polynomial, there is only one critical point which is in C. And in that case, we have two types of post-critical dynamics. Either our critical point is periodic, and this is this picture. So we apply our polynomial and eventually we return to C, or it's strictly pre-periodic. So this is this picture. So we go for some time and then we get into a periodic cycle. Now there is a, okay, so why we are looking at polynomials and why now we have complex numbers. So this is because of the following observation of Richard Pink. For number fields, the geometric profinite iterated monogenomic group can be computed over the field C of t. And in geometric group theory, there is a very well-developed area which studies iterated monogenomic groups of polynomials. These are discrete groups. They arise as fundamental groups of coverings of a punctured sphere. And it turns out that if you have a post-critically finite polynomial, then the closure of this discrete iterated monogenomic group is isomorphic to the profinite geometric iterated monogenomic group over C of t. And in geometric group theory, we have a method of describing elements of groups acting on rooted trees. There is so in particular, you can write them down recursively using the presentation of our automorphism group of the tree as the Rief product of finite groups. So, and once you have this representation, you can actually compute, and you can figure out a lot of things by just straightforwardly computing. And also an important point. So when you have a post-critically finite polynomial and you look at the iterated monogenomic group, then for every point in the post-critical orbit, you get a generator, you get an element. So if you have a point P, I'm going to denote the corresponding generator by G of P. And the dynamics of the post-critical orbit tells you basically how to write down your generator level by level up to conjugacy within the automorphism group of the rooted tree. Okay, so for the quadratic case, a lot is known. And in particular, there is a paper, influential paper by Richard Pink, which is unpublished but available on arXiv, and many people are reading it, where he gave a very detailed description of the profinite iterated geometric and arithmetic monogenomic groups in the quadratic case. So once we have this description, we can also ask, can we, for this particular iterated monotromic groups, can we study their dynamical properties? And this is the next two results I wanted to mention. So if you have a quadratic post-critically finite polynomial over a number field, let us look at the pro-finite geometric iterated monotromic group associated to that. Sorry. And let us ask, the actions we get this way, are they stable or wild? And turns out this depends very simply on the length of the post-critical orbit. So first, if you have a post-critical orbit which is just a fixed point, then the action of the corresponding Galois group, the geometric iterated monotromic group, is stable. If you have post-critical orbit of length 2, which is strictly pre-periodic, which means we apply one iteration and then we get into a fixed point, then the action of the corresponding pro-finite iterated geometric monotromic group is also stable. In all other cases of post-critically finite polynomial, the action is wild. And this can be computed. Now, what happens for the pro-finite arithmetic iterated monotromic group? Again, if you have the post-critical orbit, which is a fixed point, then the action of the arithmetic iterated monotromic group is stable. But now this discriminant invariant, which I described earlier, so for the geometric group, it was trivial. Now it's profinite. It's a profinite group, so it's bigger. If you have an orbit of length 2, which is strictly pre-periodic, then the action of the arithmetic group, profinite arithmetic group, is stable. And again, for the geometric counterpart, the discriminant invariant was finite, but now it's profinite. And in other cases, for longer post-critical orbits, which are finite, the action of the profinite arithmetic iterated monotromic group is wild. Okay, so for quadratic polynomials, we have the paper by Pink, which describes them in great detail, and you can figure out a lot about this, a lot about the associated iterated monotromic groups. But can we get this similar results in for polynomials of higher degrees? Turns out the high degree case is a lot more complicated. So let me try to explain to you what are the issues. Okay, so the issues come down to the choice of a generating set for our profinite iterated monotromic group. So when we talk about a finite generated set for a profinite group, we mean that this set topologically generates a profinite group. This means that it generates a countable subgroup which is dense in the profinite group. Okay, so now in the quadratic case, we have two critical points, infinity and some point in C. So let us just look at the orbit of this point, critical point in C. So we forget about the point at infinity for now. So using this approach from geometric group theory, to each point in the orbit of C, we can associate a generator. So R here is the length of this post-critical orbit. So the result of Pink gives us so-called model generators. So this set of model generators only depends on two things: on the length of this orbit, post-critical orbit of C, and also on the length of the periodic cycle in C. So the dynamics, the actual dynamics on the polynomials, only on the periodic cycle in C. So we write down these model generators. They generate a profinite group, and the result of pink is that you can choose some element in the group, in the automorphism group of the tree, so that you can conjugate your model group, your group generated by model generators, to your actual profinite geometric iterated monogenomic group. Now, these generators, these R generators, only correspond to the points in the post-critical orbit of the critical point in C, but we also have the point at infinity. So it turns out if you check the product of all the generators, you get the generator of the point at infinity, and turns out that this is an odometer. This is the odometer of the Adin machine. This is the type of element whose dynamics I mentioned before. So we have this in quadratic case. So what are the actual issues in the proof? When we have a iterated geometric monogenomic group, the Galois group, we can write down the generators, but they're determined only up to conjugation within this group. And the conjugating element is different for each element. So even if we start conjugating this group by the elements within the group generated by these elements HI, by the generators, what we end up may be not a generating set for the profinite group. And this is a well-known problem which motivated a lot of work in group theory or geometric group theory, and led to the notion of an invariable generating set, which I have here on the slide. So what is an invariable generating set? And it can be defined by for finite groups, countable groups, and profinite groups as well. So a set invariably generates a group if the following holds. So we have set S of generators, and we conjugate them by different elements. So if for any choice of these conjugating elements, we still end up with a generating set for G, then S is an invariable generating set. Okay, so this is the first issue. And the second issue is that even if we conjugate a generating set by a single element, we may end up with a by different elements, we may end up with generating sets which generate the same profinite group, but different countable groups. So these are two issues. Now, how do we get around these issues? For instance, in the case when we're looking at the binary tree, so when D is 2. So in this case, the situation actually turns out to be quite simple, because the following holds. If we look at our model group or at the geometric iterated monogenomic group and restrict it to each finite level, then what we get is a two-adic, so p-adic group, which is nilpotent. And from that, one can deduce that the set of model generators corresponding to this orbit of one single point is an invariable generating set for our profinite group. And so Also, if we add a point at infinity to our generating set, then we will have r plus 1 elements, and any collection of r elements from this set will be a generating set for our profinite group. So if you go to degree 3 or higher, when we restrict our profinite group to finite levels, then these restrictions need not be p-adic groups, so they need not be nilpotent. And this is where the issue lies. So there is one case in which the situation is a bit similar to what we have for quadratic polynomials in the work of Pink. And this is the case when you have a polynomial of degree d, which is unicritical. This means that it only has one critical point in complex numbers. So in that case, well, this point and also the infinity are your critical points. And in particular, if your degree d is p, you can use the same argument as Pink. If the degree d is not a prime, then there is a very recent work by Adams and Hyde, which obtains a result similar to the result of Pink. And what it says is the following. So if you have a unicritical, post-critically finite polynomial of degree d, let us look at the generators of the associated profinite geometric iterated monotromy group. And again, in this case, you can just look at the generators corresponding to the points in the post-critical orbit of this point C. And they provide for you an invariable generating set. And then you can also, So this is what happens for unicritical polynomials. So this means, again, that in particular, you do not have to worry too much about the point of infinity, about the generator around the point at infinity, which is also an odometer. Now, what happens when our polynomial is not unicritical? So this is recent work with Dean Wardell, who is my PhD student here at Leiden, and Mikhail Khulchenko, who is a postdoctoral researcher at the University of Amsterdam. Okay, so we look at post-critically finite cubic polynomials over a number field. And as before, we have the post-critical set. Now let us include the infinity. So we have some assumptions, but they're not very restrictive. So the set of polynomials which satisfies these assumptions is big. So there is only a couple of cases excluded. So in this case, we discovered a new phenomenon. So when you look at the generators corresponding to, of the iterated profinite geometric monodromy group, associated, which are written down using this method, when you look at the post-critical orbit of critical points, now including infinity, turns out, in this case, you cannot exclude the point at infinity anymore. So you must have an odometer in your invariable generating set. So this is our theorem. So for cubic post-critically finite polynomials satisfying our assumption, we can find the set of model generators, which now must include the generator corresponding to the point at infinity. It must include an odometer. And this generating set of model generators provides an invariable generating set for the profinite iterated geometric monotromy group. And this set actually gives us model generators, which means that we can find an element W, which conjugates the group generated by the model generators to the geometric profinite, to actually the group associated to the profinite group associated to our polynomial. And we actually think that you can make this set a little bit smaller. You can throw out one element, but you can never throw out the generator corresponding to the point at infinity. So this is a new phenomenon which we describe in our paper. Okay, so now what about the classifying invariants, the dynamical invariants? Well, another result in this paper is that for the class of polynomials we consider, the associated profinite geometric iterated monotromy group is regular branch. I'm not going to explain what that is because I'm out of time already, but the point is that regular branch groups, their action is always wild. So for this set of polynomials, dynamically, the actions of the profinite iterated geometric monodromy group, and therefore also of the arithmetic ones, they are all wild. Okay. So these are the results I wanted to present to you today, and maybe a little bit about open problems. So this work is interdisciplinary. We approach objects which arise in number theory from the point of view of dynamical systems. Of course, we can write down a lot of concrete questions which can be solved, which are doable, computable, and so on and so on. But I think the most interesting question is actually to make a deeper connection between these two fields. In particular, it would be great to know if there are any difficult problems in number theory which we can use, which we can solve using purely topological dynamical techniques. Or the other way around. Are there any problems in dynamics of foliation theory which can be used, solved using this connection via the arboreal representations? So I think this is a very interesting question. And if anyone has ideas, I would be very happy to hear that. And this is all I wanted to say. And these are some of the references I mentioned today.